So when we look at the dead loads on this sign, we can simplify it a bit, because all the loads from the top half are going to be transferred as point loads to the ends of this horizontal member. So this sign is going to transfer loads through the connections to the vertical supports, and in turn all the loads are going to be transferred down there. So we can kind of, for simplicity's sake, ignore this top bit and just concentrate on the section at the bottom. So we have 2 point loads which are transferring the load from the top onto this beam. And let's look at the bending behaviour of this beam, see how it works. Obviously we have 0 moments on either end, and as we move away from these loads, let's give the load a quantity. Let's call it W for each of these point loads. As we move away from them, the lever arm to their line of action is going to increase. So if we call the lever arm X, then the moment at any given point is going to be W the load times X the lever arm. And the lever arm will increase, so the moment will increase linearly. And you can see I've drawn this on the top, and that's basically a convention which says that you should draw the bending moment diagram on the tension side of the member in question. And there's going to be tension on the top because the member is going to want to bend downwards. Now it's symmetrical as well, so you're going to have the same thing on the other side. And that's the bending. There's not going to be any bending in this column because we've got perfect symmetry. So if you will, one side is going to want to bend the column this way, one side is going to want to bend the column the other way. They're going to completely cancel out, so we're going to get no net bending in this column. But what is going to happen is these loads are going to be transferred via the bending to this column, and this column is going to go into compression. So it's going to need a vertical upwards reaction force. No.
Whoa,
Oh, dropped my pen. Yes, as I was saying, the reaction is going to be double each of these because they're both added together, so it's going to be 2W. And there we are, that's how the load is transferred to the ground via bending. So let's quickly look at the shear forces we're going to have. Now, you can tell a lot about the shear force from the shape of the bending moment diagram, and because the shear force is the first derivative of the bending moment, we can basically look at this slope, qualitatively work out what the slope is, and use it to draw the shear force diagram. So you can see that this slope is increasing at a constant rate. So the gradient is going to be a constant, it could be a number like 2 or 3 or whatever. So that means that the value of the shear force in this section is going to be constant, it's going to stay the same, whatever number it is. But when we get to this section here, the gradient changes. The gradient goes from a positive gradient to a negative gradient. So if this gradient was 3, then this would be -3. And what that means is the shear force is going to change side on the diagram. So let's draw that now just to explain it, because that might have been a bit convoluted. We have a constant value of shear, and then whatever side that was on, this one is going to be the other side. It's going to be negative, if you will. There you go, that's your shear force. When we look at the dead loads for this Viper Room sign, we're going to simplify it a bit and just realise that the loads are going to be transferred from the sign itself, from these vertical members, down to this horizontal member here as point loads which are going to act on the ends. So this load is going to be transferred through the 4 connections we have to the verticals. That's going to go down to the horizontal. I'm repeating myself, but it doesn't matter because I've got the camera. Hopefully the microphone's on, so we're going to be fine. Now this is going to bend right all the way down to there, hit the ground, and that's how the load goes to the ground.